Humanity's future may not be on any planet at all. We are on the cusp of a fundamental shift, moving beyond the ancient cradle of planetary surfaces to build our own worlds in the void. This is the promise of the ONeill Cylinder, a visionary concept for permanent, self-sufficient space colonies. By the end of this exploration, you will understand the complete blueprint for the first truly independent, free-floating space nations. We will uncover how a physicist's simple question in the 1970s led to a design for artificial gravity and sunlit valleys inside a rotating canister, and we will confront what it means for a society to declare its own laws far from Earth. What does it take for a civilization to outgrow its home, but to understand why we would even consider building such immense structures? We must first confront the limitations of the worlds we already have. The planets in our solar system, Earth included, present a series of bottlenecks for a truly spacefaring civilization. It begins with the simple, brutal physics of the gravity well. Launching anything from the surface of a planet is an enormous energetic expense. Every gram of material, every bolt, every liter of water must be hurled upward against the relentless pull of gravity, a process that consumes vast resources and limits what we can build. It is like trying to construct a skyscraper while having to haul every single brick up from the bottom of a deep, slippery pit. This constraint alone makes large-scale development on another planetary surface, like Mars, a staggeringly difficult proposition. We would be building our future at the bottom of another well, just a slightly shallower one. Then there is the issue of real estate itself. While a planet's surface seems vast, it is ultimately a fixed, two-dimensional sheet. All usable land, all resources, all living space is confined to that thin skin. On Earth, we are already navigating the complex challenges of sharing that limited surface. The idea of claiming and settling land on another world brings with it a host of geopolitical questions that could easily reignite old terrestrial conflicts in a new arena. Who owns the plains of Mars? Who controls the mineral rights? The very act of planetary settlement threatens to export our most enduring problems along with our hopes. Furthermore, planetary environments are fragile and singular. Terraforming Mars, for instance, is often discussed as a long-term dream, but it is a project of geological timescales, requiring us to rebuild an entire world's atmosphere and magnetosphere from scratch. It means committing to a single, enormous gamble on one environment, and what of Earth itself? Our home planet is a breathtakingly complex and delicate biosphere. Tying humanity's entire future to it is a profound risk, as our own history shows through periods of significant global change. Placing all of our civilization's eggs in one planetary basket, whether that basket is Earth or Mars, seems an unnecessary vulnerability. So the core problem becomes clear. Planetary surfaces offer gravity and possibly some resources, but they trap us with their physics, limit us with their fixed geography, and constrain us with their political and environmental fragility. They are not launch pads for exponential growth, they are containers. If humanity is to expand in a way that is truly sustainable, open, and secure, we need a habitat solution that breaks free from these ancient limitations. We need a home that is not at the bottom of a well, but built in the open space where our future truly lies. This search for an alternative led a brilliant physicist to ask a question that would change everything. In the early 1970s at Princeton University, Gerard K. ONeill was not a starry-eyed dreamer but a respected experimental physicist working on particle colliders. The world around him was a fascinating crossroads. The Apollo moon landings had just proven that human spaceflight was possible, yet the program was ending. The new focus was the space shuttle, pitched as a practical, reusable truck for low Earth orbit. At the same time, a growing environmental movement on Earth was highlighting the limits and fragility of our planetary biosphere. It was in this atmosphere of constrained ambition and ecological concern that Professor ONeill posed a deceptively simple question to his undergraduate physics students. He asked them to set aside science fiction and use real physics and engineering to evaluate a fundamental issue. Is a planetary surface the right place for an expanding technological civilization? The students, armed with slide rules and fresh perspective, ran the numbers. They calculated the energy costs, the material requirements, and the physical possibilities. Their surprising answer was a resounding no. The team concluded that building large-scale habitats in free space was not only feasible but actually easier than trying to terraform or settle another planet. This was the spark. ONeill, energized by these results, moved far beyond a classroom exercise. He launched a series of rigorous summer studies, bringing together top minds from engineering, architecture, and space sciences. They systematically designed what they called space colonies. They weren't sketching vague domes on Mars. They were engineering complete, closed ecological systems intended for the stable points in space known as Lagrange points, where the gravitational pulls of Earth and the Sun balance out. Out of these detailed studies emerged the iconic design we now associate with his name, the ONeill Cylinder. This was not a moment of wild speculation, but a deliberate, peer-reviewed blueprint for the high frontier. It presented a vision where humanity's future was not about clinging to other rocky spheres, but about learning to build and garden inside sunlight-filled islands of our own creation. The design that emerged from those studies solved the most fundamental problem of living in space with elegant simplicity. To build a home away from Earth, you must bring gravity with you. Long-term exposure to the weightlessness of orbit leads to severe health issues, from muscle atrophy and bone density loss to cardiovascular problems and fluid shifts that affect vision. Even the partial gravity of the Moon or Mars, while better than zero gravity, is an unknown. We simply do not know if humans can live, be born, and thrive for generations under 1/3 or 1/6 of Earth's pull. The ONeill Cylinder provides a definitive answer by creating its own full, Earth-like gravity through the physics of rotation. Think of swinging a bucket of water in a circle over your head. The water stays pressed to the bottom of the bucket, not because of magic, but because of centrifugal force. The cylinder applies this principle on a monumental scale. It is a massive canister several miles long that rotates steadily around its central axis. Everything on the inner surface of the cylinder, the land, the rivers, the buildings, and the people, is flung outward toward the rim, creating a steady, familiar sensation of weight. You would stand on that inner landscape with your feet pointing outward toward space and your head pointed inward toward the central axis. The entire cylinder becomes a rolling, inside-out world. But the physics of this spinning world introduce a critical design constraint. The speed of rotation and the size of the cylinder are intimately linked. A small cylinder spinning very fast can produce Earth gravity, but it would create a disorienting and nauseating problem called the Coriolis effect. In a small, fast-spinning environment, if you dropped a ball, it would appear to curve strangely sideways as it fell. If you tried to throw a baseball or simply turn your head quickly, the fluid in your inner ear would sense conflicting motions, leading to dizziness and discomfort. To avoid this, to create a stable, natural-feeling environment, the cylinder must be enormous. The classic Island 3 design proposed by ONeill called for a cylinder 20 miles long and 4 miles in diameter, rotating about once every 2 minutes. This vast scale ensures that the curve of the landscape is gentle, almost imperceptible, and the Coriolis forces are minimized to harmless levels. The choice, then, is not just about having gravity, but about having gravity that feels right, that allows for normal movement, for playing sports, for watching water flow in a straight line down a stream. It is the difference between living in a functional machine and living in a world that truly feels like home. This requirement for immense size is not a drawback, but the very feature that unlocks the potential for a real civilization, with spacious valleys, open skies, and room to grow. The sheer scale of the ONeill cylinder is what transforms it from a mere shelter into a genuine landscape. The classic design, often called Model 1 or Island 3, is built on a principle of harmony and balance. To function properly, these immense habitats are constructed in pairs, two cylinders spinning in opposite directions. This counter-rotation is a stroke of engineering genius, cancelling out any gyroscopic wobble that would otherwise make the entire structure difficult to steer or keep stable in its orbit. Picture two colossal soda cans, each 20 miles from end to end and 5 miles across, connected at their ends and twirling in opposite directions like a perfectly synchronized dance. This paired configuration is the stable foundation for everything that comes next. Step inside one of these cylinders, and the vista would defy all expectations of life in space. You would not be in a cramped metal tunnel. You would be standing in a sunlit valley that stretches to a curved horizon, with a gentle arc of land rising up on either side until it meets a strip of brilliant blue sky overhead. The interior is divided into 6 long, alternating strips that run the entire 20-mile length. 3 of these strips are land, vast tracts of soil and rock that form the continents of this miniature world. They are not flat plains, but carefully sculpted terrain complete with rolling hills, forested mountains, and large, placid lakes or rivers designed for both beauty and ecological function. The other 3 strips are the windows to the universe, immense panels of transparent material that let in the unfiltered light of the sun. These are not simple glass windows, of course, but advanced, segmented structures strong enough to hold the air in and block harmful radiation, while still granting the inhabitants an ever-changing panoramic view of the stars, the Earth, and the other cylinder spinning gracefully beside them. The Sun itself is simulated by an ingenious system of massive, adjustable mirrors mounted on the non-rotating framework outside the cylinders. These mirrors capture raw sunlight and bounce it inward through the windows, creating a natural day and night cycle by simply tilting their angles. At the very center of the cylinder, running down its long axis, is the hub. Here, at the axis of rotation, the spinning motion ceases, and you enter a realm of weightlessness. This zero-gravity hub is the bustling port and industrial heart of the colony. Spaceships from Earth or from the mining outposts on the Moon or asteroids would dock here, transferring cargo and passengers without having to match the spin of the habitat below. It is also where large-scale manufacturing, the kind that benefits from perfect vacuum and microgravity, would take place. From this central hub, a system of spokes, like the cables of a giant bicycle wheel, radiate down to the inner landscape, serving as elevators that transport people and goods between the weightless port and the living world below. As you descend one of these spokes, the sensation of gravity would gradually increase from the floating freedom of the hub to the familiar, comforting weight of home by the time the elevator doors open onto a grassy field. This is not a cramped station, it is a geography, a complete and intentional world built from the ground up to feel not just habitable, but truly lived in. But this entire vision of an Earth-like interior hinges on solving one of the most critical engineering puzzles. How do you bring the sun inside? A rotating metal cylinder by itself is just a dark, airless tunnel. For it to become a living world, it needs a reliable, natural-feeling source of light and warmth that mimics our 24-hour cycle and even the passing of seasons. Simply bolting giant light bulbs to the central axis would feel artificial, draining, and psychologically stifling. The colony must feel open to the universe, not trapped under a fluorescent ceiling. The brilliant solution to this problem is one of the most elegant aspects of the ONeill design. It uses the sun itself, but in a carefully curated way. Mounted on the stationary framework that holds the counter-rotating cylinders is a vast array of enormous adjustable mirrors. Think of them not as simple pieces of glass, but as dynamic, kilometer-scale solar sails that never propel the colony, but instead gently direct its climate. These mirrors are permanently angled to capture the constant, unfiltered sunlight of space. They then reflect this raw light inward through the 3 long, transparent window strips that run the length of the cylinder's interior. This creates a brilliant, sunlit band that moves across the landscape. Here is where the ingenuity becomes truly poetic. The mirrors are not fixed. They can be tilted by a small amount, controlled by the colony's central climate systems. To simulate the passage of a day, the mirrors are slowly adjusted to redirect their beams. As the colony rotates, a mirror might focus its light through a window to illuminate the valley below, creating a bright, sunny afternoon. Then, as the rotation continues, that mirror is subtly steered so that its light misses the window entirely, plunging that section of the cylinder into night. The starry blackness of space becomes visible through the transparent strip, and the land is lit only by the soft glow of simulated moonlight, perhaps from light reflected off the colony's exterior or from carefully positioned ambient lighting. This gives the inhabitants a genuine, rhythmic day and night, dictated not by a planetary spin but by a graceful, mechanical ballet of mirrors. The control goes even further. By changing the annual tilt of these mirror arrays relative to the sun, the colony can simulate seasons. A steeper angle might concentrate sunlight into a narrower band, creating the sharper shadows and lower light of winter. A shallower, more direct angle could spread the light more evenly, mimicking the long, gentle days of summer. This allows for agricultural cycles, seasonal festivals, and the psychological comfort of cyclical change. It means a child growing up in an ONeill cylinder would still experience the crispness of an autumn morning and the lazy warmth of a summer afternoon, all orchestrated by silent, orbiting mirrors. The light is not a simulation in the digital sense. It is real sunlight, redirected and sculpted to create time itself within a world of our own making. This orchestrated sunlight does more than just illuminate the valleys. It powers the very breath of this new world. For a space colony to be truly independent, it cannot rely on shipments of air and water from Earth. It must become a living, breathing entity all its own, a closed ecological system where every molecule is accounted for and recycled. This is the ultimate life support challenge, far beyond the filters of a spacecraft. It means building a miniature, self-sustaining biosphere under a dome of stars. The most visible component of this system would be the integrated agriculture woven directly into the landscape. Those rolling hills and flat plains are not just for parks, they are vital farmland. Vast tracts would be dedicated to staple crops like wheat, rice, and potatoes, grown in deep, rich soil brought from the moon or asteroids. Orchards would line the gentle slopes, and aquaculture ponds in the lakes would provide protein. This agriculture is not separate from the living areas. It is the foundational layer of the habitat, providing food, producing oxygen, and helping purify water through natural processes. It turns the entire interior from a scenic painting into a functional, life-giving engine. Water is the bloodstream of this closed loop. Every drop is precious. Water from rivers and lakes is continuously circulated, purified, and reused. Advanced recycling systems would reclaim water from every possible source, from household wastewater to the very humidity in the air. Imagine a morning mist over a lake that is later collected, cleaned, and returned as drinking water in a cycle as perpetual as the colony's rotation. The atmosphere itself is a dynamic balance. Humans breathe in oxygen and exhale carbon dioxide. The vast fields of crops and forests do the opposite, absorbing carbon dioxide and sunlight to produce oxygen and food through photosynthesis. This creates a beautiful, reciprocal relationship, but it is a delicate one. The system must be meticulously managed, with sensors monitoring gas levels, and perhaps supplemental gardens or even algae reactors in the central hub to fine-tune the balance. The colony's biosphere would also include a carefully curated population of insects for pollination and microbes in the soil to break down waste, completing the ecological web. We have attempted something like this on Earth with sobering lessons. The Biosphere 2 project in the early 1990s was a bold experiment to create a sealed, self-sufficient environment. While it faced significant challenges, including unexpected drops in oxygen and difficulties managing food production, it provided invaluable data. It taught us that even the most carefully designed small biosphere is wildly complex with countless interacting variables. An ONeill cylinder would apply those hard-learned lessons on a much grander, more stable scale, using technology and constant monitoring to maintain the equilibrium that Earth achieves effortlessly. The goal is not to perfectly mimic Earth's chaotic biosphere, but to engineer a simpler, more robust, and utterly dependable one. Success means a civilization that has learned to tend its own world garden, ensuring that every breath and every sip of water is a testament to a balance achieved not by chance but by profound understanding. Building an island 20 miles long presents a single, staggering challenge. Where do you find the millions, perhaps billions, of tons of metal, glass, and soil? Launching it all from Earth is not just expensive, it is a fantasy that would bankrupt the world. The energy required to lift that much mass out of our planet's deep gravity makes the entire concept impossible. So if the materials cannot come from Earth, they must come from somewhere else. Gerard ONeill and his team proposed a breathtakingly elegant solution, one that turns a nearby world from a destination into a quarry. They looked at the moon and saw not a barren rock, but the construction shack for the entire high frontier. The moon's advantages are profound. Its gravity is only 1/6 of Earth's, meaning hurling material off its surface requires a fraction of the energy. It is also airless, offering a perfect vacuum for certain industrial processes. Most importantly, its soil, called regolith, is rich in the very materials needed for construction. It contains oxygen locked in minerals, silicon for glass, and aluminum and titanium for structural beams. Crucially, this loose, rocky soil is also perfect for radiation shielding. Packed into the outer hull of a cylinder, several meters thick, lunar regolith would protect the interior inhabitants from cosmic rays and solar flares as effectively as Earth's atmosphere does. But how do you move mountains of moon dirt across 250,000 miles of space? The answer is not fleets of massive rockets, but a single, ingenious machine. The lunar mass driver. Imagine a long, magnetic track laid out on the flat plane of a lunar mare. This is an electromagnetic catapult, a cousin to the maglev train. Using a series of powerful electromagnets, it would accelerate a payload-carrying capsule along its length to tremendous speed. At the end of the track, the capsule, now moving faster than the moon's escape velocity, is released. It sails silently off the lunar surface, not with a fiery rocket plume, but with the clean, precise push of magnetic force. These payloads would be simple, durable containers filled with processed regolith or raw ore. They are not delicate spacecraft, they are cosmic freight cars. Once launched, their trajectory is carefully calculated to deliver them not to Earth, but to a specific point in space where the construction site awaits. That location is a place of perfect celestial balance known as Lagrange point 5, or L5. This is a gravitational sweet spot in the Earth-Moon system, where the combined pulls of the two bodies create a stable orbit that moves in lockstep with the Moon. An object placed at L5 will stay there with minimal effort, like a ball resting in the bottom of a wide, gentle bowl. This makes it the ideal parking lot and shipyard for building something as enormous as an ONeill cylinder. Here at L5, the incoming streams of lunar material would be captured. A facility in orbit there, perhaps a growing industrial station, would process the raw regolith. Solar furnaces using concentrated sunlight would melt the soil to extract metals and spin glass for the vast windows. Automated fabricators would shape these materials into the standardized beams, plates, and components needed for assembly. The construction itself would be a slow, majestic ballet. Massive robotic arms, guided by engineers in control stations, would begin assembling the giant skeletal framework, welding and bolting the pieces together in the silent vacuum. The first cylinder would grow like a colossal crystal, ring by ring, its mirrored segments and window panels being fitted into place. This entire enterprise, from the mass driver's steady thrum on the gray lunar plains to the growing habitat at L5, forms a closed economic loop. It uses the energy of the sun and the materials of the moon to build the homes for humanity's next chapter, all without ever placing that burden on the fragile ecology of Earth. The planet becomes not a quarry but a garden we look back upon while our industry moves to the airless rocks where it belongs. The blueprint was now complete, a detailed engineering proposal waiting in the pages of academic journals. But a vision this grand needed more than equations, it needed a movement. In 1975, as the Apollo era faded into memory and the practical shuttle program dominated NASA budget, a different kind of mission was launching from a living room in Tucson, Arizona. Physicist Keith Henson and his wife, Carolyn, gathered with friends, inspired by Gerard ONeill's recently published work. They believed the future he described was not a distant dream but an achievable goal, and they decided to build a grassroots army to make it happen. They called it the L5 Society, named for the Lagrange point where they believed the first space colonies should be built. Their rallying cry was optimistic and specific, L5 in 95. They aimed to see a permanent human settlement at that celestial crossroads within just 20 years. This was not a club for scientists alone, it was a populist campaign. The society published a lively newsletter, organized conferences that mixed hard engineering with speculative art, and took its message directly to the public. They set up booths at science fiction conventions and county fairs, handing out pamphlets next to displays of prize-winning vegetables. Their argument was powerfully simple. Space colonization was not just about exploration, it was about solving fundamental human problems. It offered new resources to alleviate scarcity, new frontiers to ease terrestrial conflict, and a safeguard for the human species against planetary catastrophe. They framed it as the ultimate environmental act, moving heavy industry off the fragile Earth and into the sterile void where it belonged. This message resonated with a diverse coalition, from counterculture idealists and forward-thinking engineers to libertarians and environmentalists, all seeing in the cylinders a reflection of their own hopes for a better future. The L5 Society's most significant impact was in the political arena. They became a persistent, knowledgeable voice in early space policy debates, lobbying Congress and testifying before committees. They argued passionately against what they saw as the dead end of a shuttle-centric, low-Earth orbit strategy, advocating instead for the high frontier of permanent settlement. While their bold 20-year timetable would not be met, their advocacy was crucial. They helped shift the conversation about humanity's future in space from one of brief visits to one of permanent homes. In 1987, recognizing that their goals had broadened, the L5 Society merged with the older National Space Institute to form the National Space Society, an organization that continues this advocacy today. This transition marked a pivotal moment, the evolution of ONeill's cylinder from a fascinating theoretical design into a sustained cultural and political goal, a shared destination on humanity's long-term map. The ONeill cylinder was not the only blueprint on the drafting table. As NASA's own summer studies progressed, other compelling designs emerged, each offering a different answer to the question of what a space home should look like. Two of the most prominent were the Bernal sphere and the Stanford Torus, each with its own distinct geometry and character. The Bernal sphere, named for the scientist who first proposed a spherical space habitat, is perhaps the most visually striking. Imagine a giant globe, roughly a mile in diameter, rotating to create gravity on its inner equatorial band. The majority of the living area is a wide, curved valley that wraps around the sphere's midsection, with the landscape arching upward until it meets vast windows at the poles. The interior feels like being inside a colossal planetarium, with towns and farms laid out along a single, continuous strip. Its compact design makes radiation shielding and structural integrity somewhat easier to manage, but it also imposes a strict limit on usable land area, confining the entire world to that one curving strip. In contrast, the Stanford Torus, named for the university that helped design it, takes the form of a gigantic rotating wheel. Picture a bicycle tire 1 mile across spinning in the void. People live on the inner rim of the tire, with the landscape curving up and over their heads in a complete circle, giving the sky a distinctive, tunnel-like appearance. A central hub connects to the rim via 6 long spokes, and a massive mirror angled nearby reflects sunlight into the habitat through a ring of windows. The Torus is efficient and elegant, designed to house about 10,000 people in a relatively compact, manageable structure. Its smaller scale makes it a plausible first step, a village in space rather than a metropolis. Yet, when placed beside the ONeill cylinder, the fundamental trade-off becomes clear. Both the sphere and the Torus are essentially closed loops, offering a single, continuous strip of land. They are worlds with a fixed circumference. The ONeill cylinder, however, is an open landscape. Its 20-mile-long parallel valleys offer not just more room, but a different kind of room, space for geographical diversity, for distinct regions to develop their own character, and for the population to grow without immediately requiring an entirely new habitat. While a Bernal sphere or a Stanford Torus could serve as vital stepping stones, pioneering communities or specialized research stations, the cylinder's linear, scalable design makes it the only model conceived from the outset for something truly grand, a canvas large enough for nations to be born. Yet these vast cylinders represent more than just new homes. They are the foundation for an entirely new economic reality. The staggering investment required to build them demands a powerful justification, one that goes beyond mere idealism. The answer lies not in what we would take from Earth to fund them, but in what we would build in space because of them. An ONeill cylinder is not just a residence, it is the ultimate factory town, positioned at the heart of industries that are impossible on any planetary surface. The most transformative of these is manufacturing in the pristine environment of space itself. In the weightlessness and perfect vacuum of the colony's central hub or dedicated external facilities, the rules of production change entirely. On Earth, gravity causes convection currents in molten materials, leading to impurities and imperfections. In zero gravity, materials mix evenly and stay suspended. This allows for the creation of flawless crystals for advanced electronics, super-pure pharmaceutical compounds for life-saving medicines, and revolutionary metal alloys with perfectly blended structures, materials that are simply unmakeable on our planet. These products would be of extraordinary value, commanding high prices and creating a powerful export economy flowing back to Earth. Furthermore, the colony's location at a Lagrange point makes it the ideal shipyard for constructing the next generation of space infrastructure. Enormous solar power satellites, vast arrays that collect sunlight uninterrupted by night or weather and beam clean energy to Earth as microwaves, could be assembled in orbit by the thousands. Building these multi-kilometer structures on the ground and launching them is impractical, but constructing them in space, using materials already there, turns a dream into a logical industry. The workforce for this monumental task would not be astronauts on temporary rotation, but skilled technicians and engineers living permanently just an elevator ride away in the Cylinders valleys, commuting to work in the orbital yard. This leads to the final pillar of the economic engine, resource acquisition. While the Moon provides the bulk materials for the colony's shell, the true treasure troves are the asteroids. These floating mountains of metal and ice contain platinum, gold, cobalt, and water in quantities that dwarf all terrestrial reserves. A single metallic asteroid could contain enough iron and nickel to supply global needs for centuries. More importantly, water from carbonaceous asteroids is the oil of space, vital for life support, radiation shielding, and most critically, broken down into hydrogen and oxygen to make rocket fuel. The colonies, acting as fueling depots and processing centers, would become the ports of the solar system, enabling the economic development of deep space. The economy becomes a self-reinforcing loop. The industries require a permanent, skilled workforce, which justifies building the spacious, comfortable cylinders. The cylinders, in turn, provide the stable home base and industrial capacity to expand those very industries further. The habitat is not a cost, it is the necessary capital investment for unlocking the almost limitless wealth of space, creating an economic sphere where humanity's future is built not with subsidies, but with profit, innovation, and the products of a truly post-planetary industry. But with economic independence comes a far more profound question than engineering or industry. A collection of 10,000 or 100,000 people living in a world of their own making will not remain simply a corporate outpost or a scientific mission for long. They will be a society with all the complexities that entails. The very architecture of an ONeill cylinder plants the first seed of sovereignty, not in a declaration of independence, but in the simple, daily reality of life. These citizens are not temporary visitors, they are permanent residents born under an artificial sun, whose children may never set foot on Earth. Their world has its own day-night cycle, its own carefully managed climate, its own agricultural rhythms and industrial output. They are geographically isolated by a gulf of hundreds of thousands of miles, a journey of weeks or months. This physical and economic separation creates a psychological distance just as vast. When a crisis occurs, whether a mechanical failure in the life support systems or a social conflict within the community, Earth's governments cannot respond in time. The colony must solve its own problems, enforce its own order, and ensure its own survival. This necessity is the forge where new political identities are hammered out. The social contract, that unwritten agreement between a people and their governance, must be rewritten for a closed environment. Earthly laws, designed for continents with boundless atmosphere and sprawling frontiers, become awkward, even dangerous, when applied to a fragile island in a vacuum. Can you have the same concept of property rights when every square inch of land is engineered and vital to life support? How do you handle dissent or conflict in a place where exile is a death sentence and every individual is essential to the collective survival? The answers to these questions will not come from a terrestrial legislature, but from the community itself, developing customs, rules, and systems of justice tailored to their unique and precarious existence. Over time, these locally grown systems of governance will crystallize into a distinct political identity. The colony develops its own history, its own heroes who solved early crises, its own holidays marking the first harvest or the sealing of the hull. It cultivates cultural nuances born from its specific mix of founding populations and the shared experience of building a world. This is not rebellion, it is natural evolution. A Stanford Torus might function as a company town, and an early cylinder may begin under the charter of an Earth-based consortium. but as generations pass and the community deepens its roots into its own soil, the practical reality of self-governance blends with a growing sense of separate destiny. The habitat ceases to be a distant branch office of humanity and becomes the foundational unit of something entirely new, a free floating polity. It becomes the cell from which a space nation will grow, defined not by the dirt beneath its feet, but by the shared commitment to maintain the delicate bubble of life they have built together among the stars. This evolution from settlement to sovereignty runs directly into a legal framework designed for a different era. The rules governing humanity's activities beyond Earth were written in 1967, a time when space was the exclusive domain of two superpowers and their government flags. This document, the Outer Space Treaty, forms the bedrock of international space law, and its principles were born from a noble desire to prevent the Cold War from extending into the cosmos. It declares that outer space is the province of all mankind, free for exploration and use by all nations. Crucially, it prohibits any country from claiming sovereignty over the moon or any other celestial body by means of occupation or use. This single provision was a monumental achievement, ensuring that the new frontier would not become a scramble for colonial territory as Earth had been. It frames space as a global commons, not a prize to be owned. Yet, for the architects of a free floating space nation, this treaty presents a paradox. Its vision is expansive, but its language is anchored in the past. It meticulously addresses the activities of states on natural celestial bodies, but it is almost silent on the status of the things we might build there. The treaty does not explicitly grant or deny sovereignty over artificial structures like an ONeill cylinder. Is a massive, self-governing habitat a celestial body? Clearly not. Is it a spacecraft? The term feels absurdly inadequate for a world 20 miles long. This creates a profound legal gray area. A nation on Earth cannot plant a flag on the moon and call it territory, but could the citizens of an independent cylinder declare their man-made world a sovereign state? The treaty offers no clear answer. Furthermore, the treaty's gap regarding property rights is where theory meets economic reality. While it forbids national appropriation of celestial bodies, it does not address whether a private company or a community can own the resources they extract. Can you own the iron you mine from an asteroid or the water ice you capture from its surface? The treaty says you cannot claim the asteroid itself, but it does not say you cannot take its materials and use them. This ambiguity is the legal frontier where the first space fortunes will be made and the first disputes will arise. It sets the stage for a complex future where the principles of a common heritage must somehow coexist with the practical need for individuals and communities to own the fruits of their monumental labor, to have something to trade, and to secure the resources needed for their very survival. The old rules keep space free from earthly empires, but they provide no map for the new societies that will rise within it. The legal vacuum surrounding these new worlds is not a void but an invitation. For the first time in human history, a society could be designed from first principles, unburdened by the weight of ancient borders or inherited conflicts. The very isolation of an ONeill cylinder transforms it into a laboratory for governance, a place where political ideas can be tested with a clarity impossible on the chaotic surface of Earth. What forms of rule might flourish inside a world where every citizen understands the fragility of their shared atmosphere? One compelling possibility is a direct digital democracy taken to its logical extreme. With a population initially in the tens or hundreds of thousands, every resident could have a secure, verified identity linked to the colony's network. Major decisions, from annual resource allocation to amendments of their founding charter, could be put to a continuous, informed vote. Citizens would receive detailed briefings on the engineering and ecological impacts of each proposal, voting not as distant constituents but as direct stakeholders in their life support system. The community's survival depends on technical literacy, making a technocratic meritocracy another plausible path. Governance might be entrusted to councils of engineers, ecologists, and systems managers, individuals whose authority is derived from proven competence in maintaining the world's vital functions. In this model, leadership is not a political prize but a critical duty, a role one earns through expertise and demonstrated responsibility for the collective well-being. Yet, the economic reality of construction suggests a third model. The entity that funds a cylinder, whether a consortium of nations or a megacorporation, will initially hold immense power. The early decades could resemble a corporate administrative zone where rights and privileges are outlined in a detailed charter, and governance is a blend of appointed managers and elected representatives, all operating within a framework designed to ensure a return on that colossal investment. This system might prioritize efficiency and stability above all else. And then there are the revivalists. Some communities may consciously choose to resurrect historical systems, not out of nostalgia, but as a deliberate experiment. Could a modern adaptation of a classical Athenian democracy or a Swiss-style canton system function more harmoniously in a small, interconnected environment? The cylinder provides a controlled setting to find out. This freedom is the great promise. It allows for conscious societal design, an opportunity to correct for the flaws and injustices that have plagued terrestrial governments. A colony could encode radical transparency, universal access to information, and a legal system focused on restoration and community service rather than punitive isolation. But this same freedom carries a profound and haunting risk. The very features that enable utopia can also forge a dystopia. A technocratic council could slide into an unaccountable oligarchy. A corporate charter could legally enshrine a permanent underclass with limited rights. A direct democracy without robust safeguards could devolve into a tyranny of the majority over vulnerable minorities, a danger magnified in a sealed environment where dissent has nowhere to go. The most chilling possibility is a society that uses its total control over the environment not for equity, but for absolute social control, where compliance is ensured through the monitored allocation of air, water, and living space. The cylinder, a world built for life, could also become the perfect prison. This duality lies at the heart of the experiment. The blank slate is never truly blank, for it will be written upon by the ambitions, fears, and values of its founders. The question for any space-born nation will not simply be how to govern, but how to build a system that protects liberty within a vessel whose walls are also the boundary of survival. The sky above is a masterpiece of engineering, but it is also a constant, gentle reminder. Every resident knows on some level that the blue expanse arching overhead is a carefully maintained illusion, a layer of atmosphere held in by transparent armor. This awareness creates a unique psychological landscape, a blend of profound security and subtle vulnerability. The community is safe inside its technological womb, yet utterly dependent on the systems that sustain it. This shared dependence can forge an unprecedented social cohesion, a powerful sense of collective destiny. Your neighbor is not just someone who lives down the lane. They are a fellow systems technician, an agricultural specialist, or a teacher for your children, all essential threads in the fabric keeping the world alive. Social bonds are reinforced by mutual necessity, potentially creating a society with remarkably low crime and high levels of cooperation, where everyone understands that the success of the individual is inextricably linked to the health of the whole. Yet, this same closed environment can magnify social pressures to an intense degree. There is no wilderness to escape to, no anonymous city in which to disappear. In a cylinder, everyone is a known entity and conflicts lack a physical outlet. A personal dispute between two families or a disagreement between cultural factions cannot simply dissipate into a vast landscape. It echoes within the curved walls. The management of conflict becomes a critical social technology, perhaps more vital than any life support system. Traditional punitive justice, like long-term imprisonment, places an unsustainable burden on a closed society, consuming resources and removing productive members. Instead, these communities would likely develop sophisticated, restorative approaches focused on mediation, community service, and rehabilitation. The goal would be to repair the social tier, not just isolate the cause of it. Mental and emotional well-being would be treated with the same seriousness as physical health, with accessible support networks and spaces designed for solitude and reflection, recognizing that the psychological pressure of a manufactured world requires its own form of maintenance. Within this context, art and culture cease to be mere decoration. They become the tools for building a soul. The settlers bring the music, stories, and traditions of Earth, but under the artificial sun, these elements will transform. New artistic movements will emerge, inspired by the unique environment. Paintings might capture the surreal beauty of land curving upward into sky, or the stark majesty of the starry view through the window strips at night. Music could incorporate the deep, resonant hum of the colony's rotation or the silence of the hub, creating soundscapes impossible on Earth. Storytelling would grapple with new mythologies, tales not of ocean voyages, but of the great construction, of the first child born under the mirrored light, of the meaning of home when your entire world is a vessel. Cultural festivals would mark the colony's own milestones, the anniversary of first pressurization, or a holiday celebrating the balance of the atmospheric systems. Through this creative expression, the inhabitants do more than pass the time. They actively weave a distinct spacefaring identity. They answer the fundamental question of who they are, not as temporary exiles from Earth, but as the first generation of a people who belong to the islands they have built. Their culture becomes the living record of their choice to live in a world of their own design, a testament to the human need for meaning that persists even when the sky itself is made by hand. The profound beauty of a world under glass carries with it an equally profound vulnerability. Every window that lets in the sun, every mirror that directs it, and every pipe that carries air and water is not just a component of life, it is a potential point of failure in an unforgiving environment. For a free-floating space nation, security is not a matter of border patrols, it is existential engineering. The very systems that make the cylinder a paradise also outline its defensive perimeter in stark terms. A sustained puncture in a window strip could lead to catastrophic decompression. A coordinated attack on the external mirror arrays could plunge the colony into permanent darkness and freezing cold, collapsing its agriculture and climate within days. Sabotage of the water recycling or atmospheric processes would trigger a slow, agonizing crisis. These are not the vulnerabilities of a city, which can be evacuated or reinforced, but of a spacecraft the size of a mountain, where every citizen lives inside the machine. This reality makes the concept of defense not a choice, but a fundamental pillar of survival, forcing a difficult paradox upon these new societies. To ensure their peaceful existence, they may feel compelled to prepare for conflict. The strategic landscape they occupy adds another layer of complexity. Positioned at a stable Lagrange point, a colony holds a position of immense value, a gravitational parking spot that serves as a crossroads for travel and a platform for industry. Controlling such a point offers significant advantages, making it a strategic high ground. This naturally leads to a classic dilemma of geopolitics, now projected onto a celestial scale. If one habitat or alliance begins to deploy defensive systems, others will feel compelled to follow, if only to deter aggression. What begins as point defense lasers, designed to vaporize incoming micrometeoroids or debris, could be scaled into weapons. Kinetic projectiles, simple slugs of metal accelerated to tremendous speeds, could be launched from vast distances with devastating effect. The clean, silent void of space offers no friction or atmosphere to slow an attack, making every conflict potentially decisive and swift. An arms race in orbit would be unlike any on Earth, with the added horror that any exchange could instantly render multiple world cylinders uninhabitable, killing millions not with explosions, but with the silent, swift kiss of vacuum. This pushes the foundational ideals of these communities into a harsh light. Founded on principles of sustainability and conscious design, they now face the ancient specter of the security dilemma. How does a society dedicated to peace and the preservation of life justify building the capacity to end it? The answer may lie in a redefinition of defense itself. The primary threat might not initially be other habitats, but rogue asteroids, industrial accidents, or the cascading debris from a conflict back on Earth. Therefore, a robust planetary defense network capable of tracking and diverting hazardous objects becomes a non-controversial, universally beneficial first step. This shared infrastructure could form the basis for treaties and mutual defense pacts, a collective security framework where the defense of one habitat is linked to the defense of all. Transparency in capabilities, shared sensor data, and open inspections could become currencies of trust. The ultimate defense for a space nation may not be a bigger weapon, but a deeper interdependence, weaving a web of economic and ecological ties so dense that an attack on one would cripple the systems upon which all depend. Yet this ideal rests on a fragile hope. The tragic lesson of history is that when survival is perceived to be at stake, idealism often yields to pragmatism. The great test for these new nations will be whether they can invent a form of politics strong enough to break this cycle, to secure their fragile bubbles of life without forever looking down the barrel of a gun pointed from the stars they once dreamed of calling home. Gerard ONeill's vision was a product of its time, conceived with slide rules and the material science of the 1970s. But a blueprint is not a final product, it is a starting point for iteration. In the decades since, engineers and architects have revisited the cylinder, refining its shape for the realities we now understand better. One of the most influential modern reinterpretations is known as the Kalpana One, named in honor of astronaut Kalpana Chawla. This design makes a critical adjustment to the classic form. Instead of a long, narrow tube, Kalpana One is a shorter, wider cylinder. Think of it as moving from a traditional soda can shape toward something more like a stout barrel or a large drum. This change in proportions is driven by fundamental engineering. A shorter, wider cylinder has vastly superior structural stability. It resists bending and vibrational stresses more effectively, especially during its spin-up phase or if it needs to adjust its rotation. The internal landscape changes as well. The horizon would curve upward more noticeably, creating a more intimate, valley-like feel. But the trade-off is a habitat that is inherently stronger and potentially easier and safer to build as a first-of-its-kind structure. Kalpana One represents a shift in philosophy, prioritizing robust feasibility as the essential step toward grander dreams. It asks a practical question: what is the smallest, sturdiest version of this world we can confidently build first? The answer might be a compact, 1-mile-wide cylinder housing a few thousand pioneers, a proof-of-concept village that validates the entire principle before we scale up to continental landscapes. This evolution in design is propelled by an even greater revolution in the tools and materials we now have at our disposal. ONeill's team calculated with steel and aluminum in mind. Today, we glimpse the potential of materials that sound like science fiction but are emerging in laboratories. Carbon nanotubes and graphene are orders of magnitude stronger and lighter than the best steel. A hull woven from such materials could be far thinner, lighter, and more resistant to micrometeoroid impacts, radically reducing the mass of material we need to launch from the moon. Imagine the skeleton of the cylinder not as solid beams, but as a delicate, hyper-strong lattice, like the bone structure of a bird, achieving immense strength with minimal weight. This changes the entire economics of construction. Concurrently, the workforce building these structures will look nothing like the construction crews of the 20th century. Advances in automation, robotics, and artificial intelligence mean that the dangerous, precise work of assembly in the vacuum of L5 could be performed by swarms of intelligent machines. These wouldn't be simple remote-controlled arms, but autonomous systems that can coordinate with each other, diagnose problems, and adapt their construction plans in real time. An AI overseer could manage the entire logistics chain, from scheduling the arrival of lunar material shipments to directing robotic welders, ensuring that every piece fits perfectly with breathtaking efficiency. What ONeill envisioned taking decades with human crews might be accomplished in years by a silent symphony of machines working ceaselessly in the airless dark. These technological leaps do more than just make the cylinder possible. They transform its very nature and potential. With stronger materials, we could design larger window areas, making the interior feel even more open and less artificial. Advanced environmental systems, managed by sophisticated AI, could maintain the ecological balance with such precision that the risk of a Biosphere 2 style imbalance plummets. The habitat becomes smarter, more responsive, and more resilient. Furthermore, the ability to process materials in space with greater efficiency, perhaps using focused solar energy or advanced chemistry, means we could utilize a wider variety of asteroid resources, moving beyond simple regolith for bulk mass to tailored composites for specific structural needs. The updated vision, therefore, is not a rejection of ONeill's dream, but its maturation. It is the original blueprint redrawn with finer pens, using a palette of new technologies that turn staggering challenges into complex but solvable engineering problems. The cylinder is no longer a static image from a 1970s textbook, but a dynamic concept evolving in step with our own ingenuity. It reminds us that the greatest asset we bring to the stars is not a single perfect design, but our relentless capacity to learn, adapt, and improve upon the dreams of those who first dared to look up and sketch a home among them. The dream of the cylinder has always been a question of will, not just physics. For decades, that will was assumed to belong solely to governments, to the slow-moving machinery of national space agencies. But a seismic shift has occurred, one that has fundamentally rewritten the timeline for humanity's future in space. The driving force is no longer a single nation's flag, but the ambition and capital of private individuals, each with a radically different vision for where we should go next. Two figures stand at the forefront of this new era, their rival philosophies defining the coming century's debate. Elon Musk with SpaceX champions a future firmly anchored to planetary surfaces. His stated goal is to make humanity a multi-planet species with Mars as the primary target. He views planets as the natural, ready-made foundations for civilization, arguing that we must learn to live on other worlds to ensure our long-term survival. His entire architecture, from the reusable Starship to the planned Martian city, is engineered for landing on and taking off from rocky bodies. It is a future of domes on red deserts, a direct continuation of the Apollo ethos of planetary exploration, scaled to the level of settlement. In stark contrast stands Jeff Bezos and his company Blue Origin. Bezos is perhaps the most prominent and vocal modern advocate for Gerard ONeill's vision. He has explicitly stated that he believes the future of humanity is not on planets, but in free floating space colonies. He envisions a future where millions of people live and work in space, not as explorers on a hostile frontier, but in comfortable Earth-like ONeill cylinders. For Bezos, planets are useful as sources of raw materials and heavy industry, but they are not where humanity will primarily reside. He sees them as preserves, places we visit but do not fundamentally alter. while our civilization expands into vast, manufactured habitats in the inner solar system. This philosophical clash is more than academic. It is shaping the technological roadmap. Musk's Mars focus drives innovation in heavy-lift planetary rockets, life support for barren worlds, and in situ resource utilization to extract water and air from Martian soil. Bezos's cylinder vision, however, prioritizes a different set of technologies: reusable heavy-lift vehicles for Earth orbit, methods for processing lunar and asteroid resources, and the foundational industrial capacity in space needed to begin construction. The critical point is that both endeavors, through fierce competition and parallel development, are accelerating the exact capabilities required to make a cylinder possible. The reusable rockets pioneered by SpaceX and Blue Origin are dramatically lowering the cost of access to orbit, the essential first step for any large-scale space industry. The race to develop lunar landers and establish a sustained presence on the Moon is directly creating the infrastructure for the lunar mass driver economy ONeill described. The drive to manufacture fuel in space and harvest asteroid resources, goals shared by numerous other private companies, is building the very supply chain a free floating nation would need. Private capital, with its appetite for risk and its focus on scalable solutions, is doing what decades of government study could not. It is building the industrial base. This creates a fascinating potential synergy. The Mars-focused path may develop the closed-loop life support and radiation shielding technologies needed for long voyages, which are equally vital for a permanent habitat. The cylinder-focused path may perfect the orbital construction and resource processing that would later be used to build waste stations and fuel depots for Mars missions. The competition between these visions is not a zero-sum game. It is a forcing function, compressing decades of theoretical advancement into years of tangible engineering progress. The first cylinder may not be built by a national agency following a 70-year master plan. It is more likely to emerge from this dynamic, chaotic, and fiercely competitive private ecosystem, perhaps initially as an industrial station that gradually adds agricultural modules and living quarters, evolving organically into a community. The dream of the high frontier is being bankrolled by the fortunes of the present, turning a physicist's blueprint into the business plan for the next chapter of human civilization. The grand vision of a 20-mile-long world cannot be the first step out the door. It is a destination, a promise that lies at the end of a long and deliberate staircase. Before we can build a nation, we must first construct a workshop, a laboratory, and a neighborhood. This practical pathway begins with the orbital infrastructure we are already learning to assemble, scaled up into something far more ambitious. The International Space Station taught us how to live in space for months, even years, but it is a cramped outpost reliant on constant resupply from Earth. The next generation will be about permanence and self-reliance. We will need gateway stations not as destinations themselves, but as bustling ports and factories. These could be commercial successors to the International Space Station, perhaps built by private consortia, orbiting Earth or parked at the stable Lagrange points. They would be industrial hubs equipped with large-scale solar power arrays, refueling depots for spacecraft, and most importantly, fabrication bays. Here, in the vacuum and microgravity, the first beams and panels for larger structures could be manufactured from raw materials shipped up from the Moon. This is where we move from assembling pre-built modules from Earth to truly building with what we find in space. Concurrently, we must learn to live in rotation. Before committing to a cylinder, we will need to test the principles of artificial gravity on a human scale. The logical next step is a dedicated rotational habitat module, a spinning wheel or a short centrifuge attached to one of these gateway stations. This would not be a full colony, but a vital experiment, Scientists and engineers would live inside it for extended periods, studying the physiological and psychological effects of different rotation speeds and radii. Does a gentle spin once every 30 seconds feel natural? How do plants grow in a rotating greenhouse? Can we perfect the plumbing and atmospheric systems in a spinning environment? This test module becomes the prototype, the small-scale proof that the fundamental principle of the ONeill cylinder actually works for long-term human health and well-being. It is where we work out the kinks in a controlled, reversible setting, long before we seal the hatch on a world for 10,000 people. The ultimate intermediate stage, however, is the orbital colony itself. This is not yet a cylinder, but a significant leap beyond a station. Imagine a cluster of modules, some spinning for gravity, some static for zero-G industry, all linked together and supporting a permanent population of perhaps a few hundred. This community's primary purpose shifts from pure research to economic activity. They are the crew of a factory in the sky, manufacturing those flawless crystals or advanced alloys, operating remote-controlled mining robots on nearby asteroids, or maintaining fleets of solar power satellites. Their life support systems would be a closed-loop testbed, recycling air and water at a high efficiency, integrating advanced agriculture in dedicated biosphere modules. This orbital colony is the crucible where the social and political lessons are first learned on a manageable scale. How does a mixed crew of scientists, technicians, and their families govern itself? How do they handle disputes, allocate resources, and maintain morale when Earth is a bright blue dot in the window, close enough to see but weeks away by travel? Success here proves that a society can not only survive but also thrive and produce value far from its planetary home. Each of these stepping stones, the industrial port, the spinning test module, and the working orbital town, solves a critical piece of the puzzle. They develop the technology, validate the biology, and cultivate the social frameworks. They are the essential apprenticeships humanity must serve before we can graduate to the profound responsibility of building and inhabiting a world of our own. The first true cylinder would not be born whole, but would grow like a living thing, its skeleton laid down in the silent dark before its skin and soul were ever added. The construction sequence begins not with a habitat, but with a purpose-built machine, a bare-bones framework called the construction shack. This initial module, anchored at the stable Lagrange point, is little more than a pressurized control center and dormitory for the first crew of engineers and robot operators. Its sole function is to oversee the birth of the world it will one day be absorbed into. From this humble nerve center, the project's true foundation is launched, the central spine. This is the backbone of the entire cylinder, a non-rotating truss of incredible strength that runs along the future habitat's axis. It is the stable highway upon which everything else will be built, providing attachment points, power, and data lines. Along this spine, the first major additions are the industrial pods. These are specialized zero-gravity factories, each dedicated to a single task, one for smelting lunar metals in solar furnaces, another for spinning glass from molten regolith, a third for fabricating standardized structural beams and hull plates. These pods are the colony's prenatal organs, consuming raw materials from the steady stream of lunar launches and converting them into the building blocks of their own home. With the industrial base operational, the slow, majestic assembly of the hull can begin. Robotic arms, guided by the crew in the shack, start attaching the massive prefabricated ribs to a central hub, forming a giant wheel-like frame. This is the first rotating element, a bare skeleton perhaps only a few hundred meters across. It begins to spin, slowly at first, for stability. This initial ring is not for living. It is a proving ground and a construction platform. More ribs are added, extending the structure lengthwise, turning the wheel into a short, open-ended drum. Hull plates, curved sections of metal and composite layered with raw regolith for radiation shielding, are robotically welded into place on this growing drum, segment by segment. The cylinder expands in both directions from the center, its mirrored end caps and long, segmented window strips being installed as it grows. For years, the site is a scene of silent, orchestrated chaos, a symphony of machines under the unwavering sun, with the structure gradually stretching toward its full 20-mile span. Only when the final hull segment is sealed does the most delicate phase begin, the transformation from an empty shell into a living world. The interior is a barren, dark metal landscape. The first step is to create a breathable atmosphere. Giant tanks of oxygen and nitrogen, extracted from lunar minerals and asteroid ice, are piped in, slowly pressurizing the vast volume. As the air thickens, the immense mirror arrays on the external framework are activated, and for the first time, sunlight streams through the windows, painting moving bands of light across the raw interior. With light and air secured, the terraforming begins. Automated vehicles spread a foundational layer of processed asteroid material and nutrient-rich regolith across the floor. Then comes the soil, a carefully engineered blend teeming with bacteria and nutrients, delivered in vast bulk carriers. Rivers and lakes are carved by robotic earth movers and lined with impermeable materials before being filled with recycled water. Finally, the seeds are sown not by hand, but by specialized drones that plant forests, grasslands, and crops according to a master ecological plan. The landscape greens in accelerated time under the artificial sun. This entire process, from the first bolt on the spine to the first sapling breaking the soil, would span decades, perhaps even generations. The construction shack, its original purpose fulfilled, would likely be decommissioned or repurposed as part of the central hub, a museum piece marking where the dream began. The population would grow in phases, starting with the essential maintenance and agricultural teams who monitor the newborn biosphere, followed by the first families, the teachers, the artists. What began as an industrial project would, through the sheer passage of time and the accumulation of life, complete its metamorphosis into something far greater, a home. The final act of construction would not be the sealing of a hull, but the moment a child who knows no other world looks up at that manufactured sky and simply calls it beautiful. That single, beautiful cylinder is just the first sentence in a much larger story. Our future in space will not be a solitary island, but a sprawling archipelago. Picture not one, but dozens of habitats orbiting in the stable gravitational harbors near Earth and the Moon, a constellation of man-made worlds. Each cylinder, sphere, or torus becomes a distinct node in a growing network, a civilization no longer rooted to a single rock but distributed across the orbital realm. This is the true emergence of free-floating space nations, not as isolated city-states, but as interdependent members of a complex, decentralized society. The first and most tangible connection between these habitats is trade. While each world strives for self-sufficiency, specialization is the engine of prosperity. One cylinder, positioned favorably near lunar supply routes, might become the solar system's primary manufacturer of structural beams and hull plating. Another, with a particular expertise in closed-loop ecology, could become a renowned center for agricultural research, developing new crop strains optimized for orbital gardens and trading seed banks and botanical data. A Bernal sphere, with its unique geometry, might dedicate itself to zero-gravity pharmaceuticals, producing medical wonders impossible to formulate on Earth. Their economies become interwoven through a constant flow of goods, data, and intellectual property. Cargo craft, perhaps automated shuttles or piloted freighters, would traverse the routes between these orbital ports, carrying everything from specialized machine parts and refined metals to cultural artifacts and newsreels. This exchange creates a web of mutual dependence, where the success of one habitat directly benefits its neighbors, fostering a powerful incentive for stability and cooperation. With trade comes the inevitable need for diplomacy, each habitat, having developed its own systems of governance and social norms, becomes a de facto political entity. Relations between them would be conducted through formal channels, not with armies, but with envoys and communication networks. Disputes will arise, perhaps over resource extraction rights to a particularly rich asteroid, or concerning traffic management in crowded orbital lanes. These conflicts would not be settled by force, for the reasons we've already seen. The vulnerability of their environments makes war an act of mutual suicide. Instead, they would necessitate the creation of new interstellar law, a framework built not on terrestrial precedent, but on the shared reality of life in a fragile bubble. We might see the rise of neutral arbitration councils, comprised of representatives from multiple habitats, who mediate disputes based on mutually agreed charters. Alliances would form not for defense against external invasion, but for collective projects too large for any single habitat to undertake, like constructing a new mass driver on a distant asteroid or funding a long-range telescopic array. This political landscape would be fluid and dynamic, a constant negotiation between the pride of local sovereignty and the practical benefits of collective action. The travel between these worlds would weave the social fabric of this new civilization. While communication is instantaneous via laser links, physical travel would still hold profound significance. It might begin with official delegations and trade envoys, but would quickly expand to include artists, students, and tourists. A young person from a cylinder with a technocratic government might spend a year studying philosophy in a torus run by direct democracy. Musicians from a Bernal sphere renowned for its acoustic innovations might tour a dozen habitats, their performances adapting to the unique resonance of each interior landscape. This movement of people would act as a powerful cultural cross-pollination, preventing any one habitat from becoming too insular or dogmatic. It would create a shared identity as spacers, citizens of the high frontier, even as each community cherishes its local customs, its particular slant of artificial sunlight, and its own founding myths. The ultimate result is a civilization of a type never before possible, a truly decentralized multi-world society. It lacks a single capital, a dominant gravitational center like a home planet. Power and culture are distributed across the network, residing in the vibrant diversity of its member habitats. Some might be bustling, cosmopolitan centers, hubs of commerce and diplomacy. Others could be quiet, monastic enclaves dedicated to scientific research or spiritual contemplation. There could be habitats that choose to minimize technology, living a simpler agrarian life under their dome of stars, and others that are dazzling showcases of bio-integrated AI and augmented reality. This pluralism becomes the greatest strength and defining feature of this new chapter. Conflict is managed not through domination, but through the intricate balance of mutual need and the constant, enriching exchange of ideas and people. The free-floating space nation is not a single political declaration, but this entire living, breathing ecosystem. It is the quiet hum of the cargo shuttle docking at the hub, the animated debate in a virtual council chamber linking 10 different cylinders, and the wonder of a child gazing from one artificial world at the glittering lights of a dozen others, each a tiny star of life in the eternal night. This constellation of homes represents humanity's maturity, our transition from a species confined to a planetary cradle to one that has learned to cultivate its own gardens in the void, and in doing so, has woven a new tapestry of community among the stars. This constellation of worlds offers more than just new frontiers. It provides our species with its first true insurance policy. For all of human history, our existence has been a single, breathtaking gamble, with every life, every memory, and every achievement resting on the thin, fragile biosphere of one planet. An ONeill cylinder is not merely a new home, it is a backup for civilization itself, a strategic dispersal of humanity's flame to ensure it can never be extinguished by a single catastrophe. The threats are not hypothetical. A large asteroid impact like the one that reshaped life on Earth 66 million years ago remains a permanent fixture in cosmic probability. A supervolcanic eruption could blanket continents in ash, triggering a global winter that collapses agriculture for a generation. Even our own ingenuity has created existential risks, from the potential of a global health crisis to the shadow of geopolitical conflict. These are planetary-scale events, and their common feature is that they threaten everything and everyone in one place at one time. The profound vulnerability of having all of humanity on a single world is a risk we have accepted by default, simply because we had no alternative. The free-floating space nation changes that equation entirely. By establishing multiple, independent, and self-sustaining habitats across the solar system, we accomplish what biologists call dispersal. In nature, a species confined to one valley is vulnerable to a single flood or fire. But a species whose populations are spread across many valleys, separated by distance and geography, gains resilience. A disaster that wipes out one population leaves the others intact to recover and recolonize. This is the core safeguard. A civilization distributed across a dozen cylinders, separated by millions of miles of space, is effectively immune to any one disaster, whether natural or human-made. An asteroid that strikes Earth would be a tragedy of unimaginable scale, but it would leave the habitats at the Lagrange points untouched, their sun mirrors still turning, their atmospheres still cycling. A global health event could not leap the vacuum between worlds without deliberate technological intervention. This separation creates a firewall of cosmic proportions. The argument extends beyond mere biological survival to the preservation of our cultural and intellectual heritage. Each habitat would carry with it a vast digital and physical archive of human knowledge, art, science, and history. In a distributed civilization, this legacy is not stored in one library on one continent. It is duplicated and maintained in multiple, autonomous vaults orbiting safely apart. The sum total of human achievement, from philosophy and music to engineering and medicine, gains a redundancy it has never known. The loss of any one habitat, while a devastating blow to its community, would not erase the collective memory of our species. The others would carry on, learn from the event, and ensure that the story continues. This transforms our place in the universe from one of passive risk to one of active stewardship. Building these habitats is perhaps the most profound ethical act we can undertake for future generations. It is a declaration that we value the human project enough to secure its continuity, to refuse to let all our striving and beauty be subject to the whims of a random rock or the failures of our own politics. It moves our responsibility from just caring for the world we have to consciously building new ones to ensure that care was not in vain. The ultimate purpose of a spacefaring civilization, then, may not be conquest or even exploration for its own sake, but this deeper, more humble goal: to gently place the echoes of Earth's song into many bottles and set them sailing on the solar winds so the music can never be silenced. Yet for all its promise, this vision has never been free from serious and thoughtful critique. The scale of ambition invites a proportional scale of doubt, and confronting these challenges is essential to separating dream from destiny. The most immediate hurdle is the staggering economic and energetic cost. Launching the initial infrastructure, building the mass drivers, and assembling the first cylinder represents an investment that could dwarf the gross domestic product of entire nations for decades. Critics rightly ask if any entity, public or private, could or should marshal such resources for a project with a payoff measured in generations, not quarterly reports. The counterpoint begins with perspective. Humanity has undertaken projects of similar relative scale before, from the centuries-long construction of great cathedrals to the Apollo program, which at its peak consumed nearly 4.5% of the United States federal budget. These were not merely expenditures but investments in identity, technology, and frontier. The funds for a cylinder would not vanish. They would catalyze a new industrial revolution in space, creating technologies and capabilities with untold spin-off benefits. Furthermore, the economic model is not a one-way drain. As we explored, the cylinder enables industries like zero-gravity manufacturing and solar power satellites, which could generate vast wealth and clean energy for Earth, beginning a return on that monumental investment. The energy required is indeed colossal, but it is the energy of our sun, abundant and free in the void, not the fossil fuels of a strained planet. The initial cost is a gate, not a wall. Equally daunting is the biological challenge. We have never maintained a closed ecological system for 10,000 people, let alone millions, for centuries. Our largest attempt, Biosphere 2, struggled with unexpected oxygen drops and food shortages, a sobering lesson in complexity. Skeptics argue that we are proposing to balance a biosphere in a bottle with no room for error, where a single cascading failure could mean catastrophe. This criticism cannot be dismissed. It must be met with humility and phased engineering. We would not begin with a full cylinder. We would start with small, modular closed-loop systems on orbital stations, then scale up to a village, then a town, rigorously testing each component of the life web. The cylinder's immense internal volume is actually an advantage over a small test module, providing greater buffering capacity against fluctuations in air composition or temperature. Advanced monitoring and AI-driven management would oversee the atmosphere and water cycles with a precision impossible in Earth's wild biosphere. The goal is not to perfectly replicate nature's chaotic balance, but to engineer a more predictable, managed symbiosis, learning from each small step before taking the larger leap. Perhaps the most profound worries are social and political. A habitat where every breath is managed by central systems could become a dystopia of perfect control. What prevents a governing authority from using the allocation of air, water, or living space as tools of coercion or to enforce a permanent class system? This risk is the dark shadow of the cylinder's utopian potential. The counterargument is that this very vulnerability makes transparent and accountable governance not a luxury, but a prerequisite for survival. A population that understands its life support systems will demand oversight. The architecture of independence, the need for a highly skilled and educated populace, creates citizens who are difficult to subjugate. The history of freedom is often tied to the leverage of the governed, and in a cylinder, that leverage is the collective knowledge required to keep the lights on. Social structures would likely evolve rigorous checks and balances, not out of pure idealism, but out of the practical understanding that oppression risks sparking a conflict that could rupture the world itself. The design does not guarantee liberty, but it makes tyranny a uniquely dangerous gamble for any would-be ruler. Finally, there is the resonant ethical question: why not just fix Earth first? It feels like an abandonment, a fantastical escape from pressing problems of inequality, environmental damage, and conflict. This argument carries deep moral weight. The response is that the two endeavors are not in competition. They are complementary, and in fact, the cylinder vision directly addresses Earth's problems. The primary industrial activity to build and supply the cylinders is moved off-world, ending the need to rip resources from Earth's biosphere. Beaming clean solar power from orbit could meet global energy needs without combustion or radioactive waste. The technologies developed for closed-loop recycling and efficient agriculture would have immediate, revolutionary applications in sustainable living on Earth. More fundamentally, opening a new frontier has historically relieved social and political pressure on the old world, providing an outlet for ambition and a safety valve for dissent. It expands the realm of the possible, shifting humanity's focus from a zero-sum game over a fixed planet to a positive-sum future of growth and discovery. Fixing Earth and building new homes in space are not sequential tasks. They are part of the same long-term project of ensuring a flourishing and resilient civilization. The choice is not between one or the other, but between a future where all our hopes remain confined to one fragile world, and a future where we learn to tend our garden here while planting new seeds among the stars. The criticisms are not roadblocks, they are the essential stress tests that force the dream to grow stronger, more nuanced, and ultimately, more human. The blueprints and equations of the 1970s found their truest resonance not in government reports, but in the stories we began to tell ourselves. Long before the first mass driver could be sketched, the ONeill cylinder was being painted across the canvas of popular culture, transforming a complex engineering proposal into a shared dream. Its journey from academic paper to public consciousness began with a seismic shift in science fiction, moving the genre away from distant alien planets and toward a future built with human hands in the space between worlds. Perhaps no single work did more to cement this image in the global mind than the iconic anime series Mobile Suit Gundam, which premiered in Japan in 1979. In its universe, the sprawling, cylindrical space colonies are not mere backdrops. They are the very heart of human civilization and the source of the story's central conflict. Millions live in these rotating habitats, complete with artificial skies, cities, and countryside, while Earth becomes a distant, almost mythic green jewel. Gundam presented the cylinder not as a futuristic oddity, but as a home with all the politics, social strife, and generational identity that implies. It made the concept tangible and emotionally real for an entire generation, framing life in a manufactured world as a normal, if complex, human experience. Across the Pacific, a different vision took shape in the 90s with the television series Babylon 5. Here, the titular station was a rotating cylinder 5 miles long, a neutral port and diplomatic hub where different species negotiated and clashed. While not a full ONeill habitat with internal landscapes, Babylon 5's design wore its influences proudly. Its rotating sections for gravity, its central docking bay, and its role as a free-floating political entity directly echoed the concepts of Lagrange point colonies and space-based sovereignty. It presented a future where such structures were the essential infrastructure of an interstellar community, the airports and conference centers of the high frontier. This cultural embedding continued into the 21st century with blockbuster films. Christopher Nolan's Interstellar featured the Endurance, a rotating station with modules arranged in a ring, and its climax offered a breathtaking glimpse of a future where humanity resided in vast, cylindrical habitats near Saturn. The visuals were stark and majestic, communicating a sense of quiet rebirth, of a species that had learned to build its own arcs. On the literary front, Ian M. Banks' celebrated culture series presented the ultimate evolution of the idea. His orbitals were not cylinders, but staggering rings millions of miles in circumference, yet they shared the same philosophical DNA, artificial worlds built by a post-scarcity society for the sheer joy of living within a curated paradise. In Banks' work, the habitat is not a lifeboat, but a masterpiece, symbolizing a civilization that has mastered its environment so completely that it can devote itself to art, leisure, and complex social play. This steady drip of cultural representation has performed a subtle but profound alchemy on the public imagination. What was once a radical, almost incomprehensible idea from a physics professor has become a familiar trope, a standard piece of the visual and narrative language we use to envision tomorrow. This familiarity is not trivial, it is a prerequisite for acceptance. When an engineer today speaks of building large-scale orbital habitats, they are not describing pure fantasy. They are referencing an image millions have already seen, internalized, and even yearned for on some level. The cylinder has moved from the realm of the unimaginable to the realm of the inevitable in our collective story. This cultural groundwork has been instrumental in shaping a public perception that is increasingly open to a spacefaring future not of desolate Martian outposts, but of engineered Earths hanging in the void. It has prepared our minds to see such a future not as a cold, mechanical exile, but as a potential home filled with the same light, community, and conflict that has always defined the human experience, just under a different sky. The vision is vast, but every journey begins with a single, deliberate step. Weaving together the threads of technology, economics, and politics allows us to sketch a possible path, a speculative roadmap for how the first free-floating space nation could evolve from today's first rockets into tomorrow's sovereign world. This timeline stretches across a century and a half, not as a prediction, but as a plausible sequence of cause and effect, where each milestone unlocks the next. The first phase, already underway, is the construction of an industrial foothold. Over the next 2 to 3 decades, we will see the transition from scientific outposts to true orbital factories. The successors to the International Space Station will be commercial facilities, operated by consortia of private companies and national agencies, positioned in low Earth orbit and at the stable Lagrange point L1 or L2. These will not be habitats for large crews, but robotic workshops and fuel depots. Their primary product will be infrastructure, using the first trickles of lunar water ice and asteroid metals to manufacture simple construction materials in space for use in space. This period proves the foundational economics, turning raw celestial resources into valuable products like fuel and radiation shielding, and establishing the initial supply chains that make everything else affordable. By mid-century, around the year 2070, we achieved the second critical milestone, the first dedicated rotational habitat. This will not be an ONeill cylinder, but its essential prototype, a spinning wheel or short drum perhaps a few hundred meters across, attached to one of the industrial hubs. Its purpose is purely experimental. A permanent crew of engineers and bioscientists will live inside for years, conducting the definitive research on long-term artificial gravity. They will study bone density, cardiovascular health, plant growth in centrifugal force, and the subtle psychological effects of living under a curved sky. This module is the laboratory where we answer the fundamental biological question: can humans thrive for a lifetime in a spun world? Its success provides the green light for the next, far more ambitious stage. The period from 2070 to 2100 is the era of the demonstration colony. This is the first true attempt at a self-sustaining community, though still small in scale. Imagine a Stanford Torus or a compact Kalpana One, home to a few thousand permanent residents. Its primary purpose shifts from research to economic production. This colony is a factory town, its population working to operate zero-gravity manufacturing pods, manage asteroid mining drones, or assemble large solar power satellites. Its life support systems are a closed-loop ecosystem of unprecedented complexity, recycling over 99.9% of its water and air, with vast internal agricultural sectors that provide most of its food. This is where we learn to manage a biosphere at the scale of a village, working out the kinks in real time with a community that has no option of immediate evacuation. Politically, it likely begins as a corporate administrative zone or a special international district, governed by a charter from Earth. But as decades pass, the residents, who are now second-generation spacers born under rotating skies, will naturally begin to refine their own rules, customs, and systems for resolving disputes, laying the grassroots foundation for a unique political identity. The turning point arrives in the early 22nd century with the achievement of full economic independence. This is not a sudden event, but a gradual crossing of a threshold. The demonstration colony, through its industries, becomes a net exporter of value. It manufactures products from flawless semiconductor crystals to novel pharmaceuticals that are of such high value and low mass that exporting them to Earth or other orbital facilities pays for all necessary imports, which by now are mostly specialized goods and information. Crucially, it also begins to produce its own critical infrastructure from locally sourced materials, building new living modules or repairing its hull without Earth-sourced parts. The balance sheet tips, and the colony is no longer a subsidized venture, but a profitable, self-sustaining economic node. This financial sovereignty is the bedrock of all future political sovereignty, for it means the community can sustain its own life without asking for permission or resources from any terrestrial power. Finally, perhaps around the year 2150 or later, comes the quiet, inevitable moment of declaration. It may not be a violent revolution, but a legal and diplomatic evolution. A crisis occurs, perhaps a complex legal dispute over an asteroid mining claim, or a necessary but drastic action to maintain life support that violates the colony's original Earth-based charter. The colonial government, responding to the will of its people, makes a decision based solely on its own survival and laws. Earth-based authorities protest, but they are months away and lack the practical means to enforce their will. In that moment, the de facto reality of self-governance becomes undeniable. What follows is likely a period of negotiation, resulting in a treaty of mutual recognition. The free-floating space nation is not born from a war of independence, but from the silent, organic force of a community outgrowing its parental framework. It is the culmination of a century and a half of incremental steps, each solving a practical problem, each moving the center of gravity for human life just a little further from the home world, until one day, looking back at the beautiful blue marble in the distance, the citizens of that first cylinder realize they are no longer looking home, but across a frontier at their place of origin. Their nation is defined not by the soil beneath them, but by the shared commitment to maintain the delicate bubble of life they built together, a commitment written into their laws, their culture, and the very rotation of their world. That quiet moment of recognition would echo across the centuries. The journey from a physicist's question to a sovereign world is not merely a tale of engineering. It is the story of humanity learning to build its own context. The ONeill cylinder is far more than futuristic real estate or a lifeboat for a troubled planet. It is the foundational blueprint for our next political and evolutionary step, a tangible design for a civilization that chooses its own scale and defines its own destiny. This vision represents the ultimate fusion of extreme engineering and profound social innovation, demanding we master both the physics of rotating metal and the delicate art of living together within it. The cylinder challenges our deepest assumptions, asking us to think beyond the ancient, comforting cradle of a planetary surface and to see the open space between worlds not as a void to cross, but as a homeland to cultivate. It reframes our future from one of finding homes to one of making them, consciously and completely. This is a grand, multi-generational project, perhaps the grandest our species has ever contemplated. It will not be finished in a lifetime, nor even in a century. It asks for patience, for sustained will, and for a kind of faith in generations we will never meet. It requires the long-term thinking of cathedrals and sequoia groves, applied to the realm of starships and constitutions. The work is not just for aerospace engineers, but for ecologists designing miniature biospheres, for lawyers drafting the first inter-orbital treaties, for artists who will teach us how to sing under an artificial sky, and for every citizen who ponders what kind of legacy they wish to leave floating in the silent dark. So where does this leave us here and now, with our feet still firmly on the soil of Earth? This future is not predetermined, but it is possible. Its first foundations are being laid today in the roar of reusable rockets and the quiet hum of research labs. You have a role in this story. Engage with these ideas. Support the scientific education and policy development that makes thoughtful progress possible. Question the old assumptions about where and how humanity must live. Imagine what you, or your children, or their children, could contribute to a project that stretches across the stars. The blueprint is drawn. The next steps belong to all of us. Will we choose to remain forever a single world species, or will we take up the quiet, magnificent task of becoming gardeners of light, builders of new skies, and the first citizens of a civilization that finally learned to make itself at home in the universe?